Hello and welcome to Lesson 2. It's Computer Systems for National 5 Computing Science. In the last lesson, we described and exemplified the use of binary to represent positive integers. We also converted from binary to denary. Today, we're going to do the vice versa. I've got another presentation for you, and we're going to convert denary numbers into binary. But first, a recap. Why do computers use binary? In the last lesson, I spoke about transistors and how they're like little switches. These are millions, sometimes billions of little switches inside the CPU, and they're either on or off. In other words, 1 or 0. So this is kind of why, the quick and easy way of explaining it. There is a lot more to do with the history of computer systems. You can Google it, but you don't really need to know this. This is just for your own information. And the question I left you with was, what is the following binary number in denary? 11100010. Now, see this little space in the middle, little gap in the middle? Some people care about this. It doesn't make any difference to the number. This little space in the middle makes no difference. Just imagine it's a single 8-bit binary number, 8 digits. So how do we convert this into denary? Get my little pen here. Well, the first thing we do is we write our binary values. So we've got 1. We always start with a 1, and then we double it every time. Please excuse my handwriting. Now in an exam or when you're doing any classwork, you would write this out much neater. Because I'm kind of tight for space and I'm using my left hand and the graphics tablet and stuff like that, it's a bit bunched up, but give yourself more room. So now we've got our binary values. We add up all the values that have a 1 underneath it. I'm going a bit diagonal. So we add them all up. We've got, there we go, 226. That is the answer to this question. So this binary number is 226. And again, you would write it very legibly, very neatly. So that's going from binary to denary. How do we go vice versa? Let's say we've got the number 22. Let's use that as an example. How do we convert that to binary? We must follow a series of steps. Now, there are two main ways for converting denary to binary. There probably are more, but I'm going to show you these ways. Now, my preferred method is the subtraction method, but I'll also show you the division method. So the number 29, how do we convert this to denary? Well, first we write our binary value. So 1, 2, 4, 8, we're doubling every time, 16, 32. And when do we stop? When do we stop? We could go off into infinity, but when do we stop? How do we know when to stop? Well, look at the number. It says 29. Am I ever going to need a 32 to make up the number 29? I'm not. I'm definitely not going to need the 64, so we can just score that out. I mean, really, what I like to do is whatever number I'm looking for, as soon as I've gone above it, so 32 is the first number that's larger than 29, I'll just stop there, and I know that I'm not going to use it, so that gets a 0 underneath it. But I'm still looking for the number 29. How do I make that number? So I go to the next largest number, and I think, can I use this to make the number 29? I certainly can. So I can take 29, I can take 16 away from it because I've used it now. So 16 minus 29, that's 13. Now so this is the new target. Can I use the 8 to make up 13? I certainly can because it's less than 13. So I can take that away from 13 and that gives me 5. And at this point, I know that 5 is just made up of a 4 and a 1. So there's the 0. So 011101 is the binary version of 29. And you can double check this, right? See if you take this number and you were to convert it back into denary, 1, 2, 4, 8, 16, and we take 16 plus 8 plus 4 plus 1, and that is, that's 29. Perfect. Let's do it again with the number 153. So let's do our binary values, 1, 2, and 2, 5. Now I have gone above 153, so I can stop here. But as a heads up, sometimes you will be told how many bits that you have to write. So in this example, it might say, convert the number 153 into 8-bit binary. So if it tells you 8 bits, you would write 8 values. 1, 2, 3, 4, 5, 6, 7, 8. Oh, this is 9. So we would score this one out. We're not going to bother with that one. Now we actually know, we don't need it. So I would just put a 0 underneath it anyway because it's too big to make the number 153. And then we'll go down the line trying to find the biggest number that I can use to make 153. So can I use 128? Yes, I certainly can. It's getting a 1. We'll go 153 minus 128, and that is going to be 25. So 25 is my new target. I can't use 64, that's too big. I can't use 32, that's too big. I can use a 16 though, that's a 16. So I'll take 16 away, And that leaves me with 9. And I know that 9 is made up of 8 and 1. That's when my mental arithmetic kicks in. So this is the number. It's 0, 1, 0, 0, 1, 1, 0, 0, 1. This is the number, but if the question asked you for an 8-bit binary number, I would not include that 0, because that's 9 bits. All right, one more. 254, quite a big one. Let's write our values. 1. So again, I'm stopping at the first number that's larger than my target. I'm going to put a 0 underneath that. And the first number I can use is 128. It gets a 1. And then I do 254 minus 128. So 126 is my next target. I can use the 64. That's 62. I can use the 32. I can use that's a 16. I can use it. I can use the 8 to make 14. And I know that a 6 is made up of a 4 and a 2, so the 1, that's a 1, that gets a 0. So this is 254. 0, 1, 1, 1, 1, 1, 1, 1, 0. There we go. This is using the subtraction method. Now, the next method, the division method, I personally don't like it. I don't find it as intuitive, but some people love this method. So you choose the one that you think is best. So 29, we're trying to find the number 29. What we do is we take the number 29 and we divide it by 2. So 29 divided by 2 equals, now you're probably thinking 14.5, but we do the remainder division. So it's 14 remainder 1. I can't really explain remainder division. I don't know. It's something that was pretty standard in primary school in Scotland. But you would do, let's say, for example, you're doing 7 divided by 3. Well, that's 2 remainder 1. And that's because 3 goes into 7 twice. That's the 2. But you've got 1 left over because 3 twice is 6. You're 1 away from 7. That's remainder division. I can't explain it any better than that. I'm not a maths teacher. I apologise. So 29 divided by 2 is 14 remainder 1. Now we've got 14. 14 is the number we're dividing by. 14 divided by 2. Now that is 7. How many remainders? 0. It divides evenly in half. So 7 remainder 0. We've now got 7. 7 is the number that we divide by 2. That is 3 remainder 1. Excellent. And 3 is our new target. 3 divided by 2. That's going to be 1 remainder 1. That's an R. Remainder 1. And then we take the 1, and it's 1 divided by 2. That is 0 remainder 1. And we can stop there because we can't do, we would just be doing 2 zeros forever. So we stop as soon as we've got a 0. And then what do? We take these numbers and we write them out from the bottom to the top. So it's 1, 1, 1, 0, 1. This should be the number 29. We can double check that. That is 29. Perfect. So this is the binary version of number 29. Now you'll notice that sometimes the way I did it before, I would always have a 0 at the start because I would stop 1 above this. I think it's good practice to always add a 0 at the start. I don't know why. Once you get to higher level, you'll realize that usually numbers that start with a 0 are positive, and if they start with a 1, they're negative. But you don't need to care about that just now. I personally just like that. Usually it will tell you how many bits to do anyway. So if this said into an 8-bit binary number, well, you'd say that's 1, 2, 3, 4, 5, 6, 7, 8. You just add zeros. Anyway, this is 29. So let's try it again with the number 153. We take the number 153, excuse my awful handwriting. We divide it by 2, and I'm going to need a calculator for this. That's 76, remainder 1. So 76, remainder 1. And then we take 76 and divide it by 2, and that gives us 38. That's 38, remainder 0. And then we do 38 divided by 2. That's 19. 19, remainder 0. We do 19 divided by 2. That's going to be 9 remainder 1. And then we do 9 divided by 2. That's 4 remainder 1. And then 4 divided by 2. That's going to be 2 remainder 0. We've got 2 divided by 1. That's just going to be 1 remainder 0. And we do 1 divided... Why did I do a 1 there? Divided by 2. 1 divided by 2 is 0 remainder 1. And once we get to 0, we stop. So the number 153, we start from the bottom and we write them out on the way up. So it's 1 0 0 1 1 0 0 1. We can double check again. Let's double check it. Yes, 153. Woo! All right, one last one. We start with 254. 254 divided by 2 equals 127 with no remainders. Now we've got 127 divided by 2 equals 63 remainder 1. 63 remainder 1. 63 divided by 2. So that's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Perfect. This is the number we're looking for. Holy moly, we made it, folks. 2 methods for converting denary to binary. We've got the subtraction method and the division method. Personally, I prefer subtraction. I don't know why, I just don't like the division method because I can't do division, that's why. Subtraction's easier. Anyway, you choose the one you like and stick with it. And remember to practice. Hope you've enjoyed this one. I'll see you in the next one.